Hello, everyone, and welcome to our first talk of the seminar series from the Technical Committee on Model-Based Optimization for Robotics. And this is the first of this year's series, which is the 2024-2025 cycle. So we are happy to have Andrea and Prete opening this cycle. And we already have the next 4 speakers lined up. We're just figuring out their schedule so we can fix the dates. And you should find the list of speakers soon listed on our website as soon as we finalize their schedule. So today we have Andrea, and I just briefly introduce our speaker. Andrea, if you, in the meantime, you want to share your screen, feel free to do so. I hope you can do that. Andrea has been an associate professor in the Industrial Engineering Department of the University of Trento in Italy since 2022. Before that, he was senior tracker assistant in the same place. In 2018, he had been a research scientist at the Max Planck Institute for Intelligent Systems. And from 2014 to 2017, he was an associate researcher at l'ACNRS in Toulouse, where he was working with humanoid robot HRP2. And before then, he did his PhD and a short period of postdoc at the Italian Institute of Technology in Genoa, Italy, where he was working with the ICAP humanoid. And Andrea's research interest mainly lies in the intersection between control, optimization, and machine learning. And today he will talk about safe and efficient robot control, combining learning and trajectory optimization.
Thank you very much, Hugh. And thanks everybody for inviting me. It's a great honor to be here, sharing my research with this community that I love so much, and I'm proud to be a member of. So I hope you can hear me, see my screen well. Tell me if that's not the case, and let's get started. So I think that in recent years, we have all been amazed by the new results that we have seen that can be achieved using reinforcement learning techniques applied to robotics. And here I'm just reporting a few examples of quadrupeds, bipeds, quadrotors performing amazing maneuver, demonstrating incredibly fine motion skills. And all this has been possible thanks to the application of reinforcement learning and offline simulation for training control policies offline and then deploying them on real hardware. So I guess if you, like me, have been working most of your career on model-based control, maybe you felt like, okay, is there anything that reinforcement learning cannot do? And what's the role that trajectory optimization can have in this new world where it seems that RL policies can do just anything? And I've been wondering about this for quite a bit now. And my conclusion is that there are still 2 aspects where reinforcement learning is really struggling and where we as model-based people can say something and help. And one is the lack of efficiency. So these RL policies are trained using lots of data, lots of compute, which requires lots of energy, and depending on your hardware, maybe also lots of time. And instead, we know that trajectory optimization is way, way, way more efficient. Indeed, we can do these trajectory optimization problems even online when we do model predictive control. And another aspect is safety, because these RL methods typically do not account for constraints or account for constraints in a very loose and relaxed way. So in the end, we get these policies that we cannot really trust because they don't give us any guarantee that the constraints are going to be satisfied. And if you're deploying your policy on a safety critical applications, and I would say that most robotics applications are safety critical, then that's something we are not really at ease with. So ideally, I would like to have a policy I can trust. I can somehow certify that in certain situations, everything at least is going to be all right and constraints are going to be satisfied. So my research in the recent years have been really focused on this question. Can we use ideas from trajectory optimization and model-based control in general to make reinforcement learning policies both safe and efficient in terms of sampling, energy, and time? So those are going to be the main two topics I'm going to discuss today. And I would like to start the discussion from the issue of safety, which is very dear to me. So I don't think that safety in robotics needs a lot of motivation, but just in case you want some, well, even today in factories, we have humans and robots collaborating on a daily basis, so they need to be in close proximity. So you want the robot to behave in a safe manner. And if you look at more like distant future prospects, we might have these black box data-driven policies that are going to perform tasks maybe driven by human natural language commands, and you want to make sure that the behavior of the robot is always safe. So the robot does not collide with the environment, does not damage itself, does not collide with humans, which may be sharing the environment with it, and so on and so forth. So when it comes to safety, I think that the main tool that we have been using in robotics, which comes from control theory, is the concept of control invariant sets. So typically we model the robot as a dynamical system, which is nonlinear, and we typically model it in discrete time because that's a bit easier for doing trajectory optimization. So we have the discrete time dynamics f of xu, which gives you the next state. And we know that the state and the control inputs are typically bounded to stay within certain sets, which represent all the constraints that I was mentioning before. So if you want to ensure that your system is safe and you want to be really certain that you are safe, the main tool we have at our disposal is using a control invariant set or some variants of such sets. So a set V is a control invariant set if once you're inside V, the state can remain inside V forever. So if we want to draw it, just to have a more pictorial image of it in mind, if X is our feasible state space, this black rectangle, V is our control invariant set, which is this green set, then we know that as long as we are inside this set V, we can always remain inside. Maybe you can also enter inside V if you start outside, but that's not guaranteed. So if you know a control invariant set for your system, then the safety problem is really solved, basically. Because, for instance, you can use it in an MPC controller, where at each iteration of your control loop, you solve a trajectory optimization problem, which looks like that. It's a standard trajectory optimization problem, where the only difference, the only additional element is that we have introduced a terminal constraint to force the terminal state of our prediction to be within this control invariant set V. And we have several books and papers on MPC which tell you, well, if you have a control invariant set and you add it as a terminal constraint in your problem, then you have guaranteed recursive feasibility. So your MPC problem is always going to be feasible. So if your solver is good enough, then you're good. You're always going to satisfy your constraints, which means that your system is safe and that can be guaranteed. The problem is that, I guess, if you know this, the theory of recursive feasibility of MPC, you already know that the problem of this theory is that having these control invariant sets, it's extremely hard, except for the simplest cases, which are the cases of linear systems subject to polytopic constraints. So if you have a nonlinear dynamical system, like a robot with nonlinear constraints, then there is no way you can compute exactly one of these sets. The best you can do is compute an approximation. and use it as a terminal constraint. The problem is that if your terminal constraint set is only approximately control invariant, then all the theoretical guarantees are lost. And your problem can, in practice, become unfeasible, which means that in practice you can get constraint violation. So this does not really help you in practice to ensure feasibility. So what I'm trying to promote, and what I'm going to try to convince you today, is that we should be looking beyond control invariant sets. We have been stuck on control invariant set for decades now. Well, not so much in robotics, because actually what we do in robotics is that we don't use them at all, because they are so difficult to compute that we don't even bother. But in control theory, they've been stuck on control invariant sets for decades. And I think we should move beyond them. And the reason why we should move beyond them is that they are very computationally demanding to compute, and we can only compute them approximately, which is not good enough for ensuring safety. So we should try to find other kinds of safe sets which have weaker requirements, so that they are easier to find. And we should then find control methods, control schemes that can still guarantee safety even using these easier to find sets. So one example of such a set that I'm trying to promote is an n-step control invariant set, which you can think of as a generalization of a standard control invariant set. So if a standard control invariant set is a set so that once you're inside, you can remain inside forever, an n-step control invariant set, and here you have the definition, is a set so that if you're inside it at time 0, then it is possible to come back inside it at time k for k between 1 and n. So maybe you cannot remain inside it forever, but if you leave, it's possible to come back within an horizon of n steps. So clearly, this is a weaker condition than classic control invariance. And what I'm going to show you in a few slides is that even with this weaker condition, it's still possible to guarantee safety in MPC if you use a modified MPC scheme. But first, I'd like to spend a few words about these n steps control invariant sets. So let me show you an example. Like before, suppose you have this black rectangle, which represents your feasible state space, and then you have this green set, which is a control invariant set, but that you don't know how to compute. But you find an approximation to this set, which is this red set V hat. So this set V hat, it's an approximation of a control invariant set, and it is not control invariant itself. Why can we say so? Well, because if we start inside V hat, we may reach the state xi, which is still inside V hat. But from xi, no matter what we do, we cannot remain inside V hat, but we are forced to leave the set V hat. But the good news is that if we take another step, so after 2 steps, we can come back inside V hat. So in this example, V hat would be a 2-step control invariant set. Let me show you some other example. Let's take a very simple dynamical system, a double integrator with simple, you have position limits and velocity limits. And here we can see in green, this light green rectangle represents the feasible state space. Then you have this a bit darker green shape, which represents the largest control invariant set. And suppose that you want to find a control invariant set that is a sphere, a circle. Well, if you do that, the largest control invariant set that you can find for this system is this one. So if you make it any larger, is not control invariant. But if instead of using control invariance, you use n-step control invariance, you may find a larger set, like this one. For instance, this circle, which is larger than the other one, is not control invariant, but it is 65-step control invariant. And we can see, for instance, that if you start from this state here on the boundary of the set, you can come back to the set in 65 steps by following this, this dark trajectory here, this black trajectory. So switching from control invariant to n-step control invariant may allow you to find bigger sets. And even more importantly, as you can have cases like this one I'm showing you in this slide, where for the family of sets, for the parametrization of sets that you're trying to use, there exists no control invariant set belonging to that parametrization. For instance, for the same system, if instead of using a circle, we use a rectangle, there exists no control invariant set with a rectangular shape. But if you look at n steps control invariant sets, then they do exist. For instance, here we can see a rectangular set, which is a 40-step control invariant set for this system. So maybe you find a bigger set, or maybe you find a set in cases where actually there did not exist any set with that shape that was control invariant. So now that we have seen a couple of examples motivating why this kind of sets may be a better choice for ensuring safety, let me discuss a couple of MPC schemes that can work with these sets, giving you strong safety guarantees. The first one I want to discuss is this receding constraint model predictive control, which is an idea that we presented this year at ICRA. And let me show you how this works with an illustration. So suppose you're at time step 0, and you have a hard terminal constraint represented by this, this red circle here, which forces the last state of your MPC horizon to be within a given set. So you predict a trajectory, which ends in that set. Then you execute the first command, which makes you reach the predicted state x1. And then you ideally would like to repeat this process over and over. The problem is that if your terminal constraint set is not control invariant, and you keep using it as a terminal constraint, at a certain point, your problem may become unfeasible. So what we thought it would be a good idea to do is, let's not keep the constraint on the terminal node of my horizon, but let's it recede along the horizon. So if we move it backward by one time step, then it's at the same absolute time it was before, which means I can be sure that this constraint is feasible, because I already have a solution that reaches this set in that horizon. So I can keep shifting the constraint backward as I keep moving forward along my MPC iterations, being sure that I'm always feasible. The problem, if I do that, is that eventually the constraint recedes, and it reaches time 0, which is my current time, and then it can no longer recede. So we need to add something to make this a tractable approach. So what we did is that we introduced a second constraint, which is a soft constraint, actually, which I'm going to represent with a light blue circle. And I'm going to use that as a terminal constraint. So I have my hard constraint that recedes along the horizon, and I have a soft terminal constraint which remains always there. So what the system is going to do is that whenever it's possible, it's going to satisfy the terminal constraint. But if it's not possible, it's going to violate it. Like, for instance, in this case, the terminal constraint is violated, but that's not a problem because it's a soft constraint. So the problem is still feasible. And then I keep doing the same. It's violated again, no problem. But then if the constraint is satisfied at a given time step, then what I can be sure that at this point in time, I can be within the set. So at the next iteration, at the next MPC loop, instead of receding my hard constraint, I can now move it forward on that state there. So it's going to be time step n-1 in my prediction. So in this way, my constraint is going to recede sometimes, but then once in a while, it's going to move forward. So I can keep doing it indefinitely. And it turns out that if my constraint that I use both as a receding and a terminal constraint is an n-step control invariant set, I can guarantee that this approach is recursively feasible, and so safety is guaranteed. So that was our first idea. Then this year, actually, we presented a second approach, which shares some similarity with the first one, but that is somehow better because it exploits parallel computation for improving safety. So this is called parallel constraint MPC, and we submitted this this year to ICRA 2025. So the idea of parallel constraint MPC is very simple. Suppose that you have a computer which has several CPU cores, so you can solve a bunch of MPC problems in parallel. What you can do is that you can instantiate a problem for each time step you have in your horizon. And in each problem, you constrain the state at a different time step to be within your safe set. Then you solve all these problems in parallel. So the overall computation time is the same of solving a single problem because they're all independent. You can solve them in parallel without any relationship between them. And then out of all the solutions that you get, you pick the best one. For instance, you take the solution where you're satisfying this constraint the furthest along the horizon, which is going to give you safety for a longer time. So this requires more computation. It's a bit more computationally demanding, but it turns out this is actually achieving better performance than the previous receding constraint MPC, as I'm going to show you in the results in a moment. So let me show you some results that we achieved with these methods. So we took as a benchmark some simulations with this Z1 robot manipulator, and we tested different MPC formulations comparing them. We use Akados as a software library for computing MPC. And the task that the robot had to achieve was to reach this target represented by the green ball, which is located on top of a table, while avoiding collisions with the obstacle, which is this other ball on the table, and also avoiding collision with the table itself. So it might seem like a relatively easy task, but actually, if you use a standard MPC formulation, it can be surprisingly high the number of times where you hit constraints. So for computing the safe set, we have used a method that we presented a couple of years ago in a RAL paper, where we use a neural network for representing an approximation of a safe set. And for each MPC formulation, we repeated 500 tests from random initial configurations to have some statistics about how often each approach was able to complete the task. So the maximum horizon that we used for these MPC formulations was 45, because that was the maximum to achieve a computation time that was below the time step of our controller, which was 5 milliseconds. So here in this plot, I'm summarizing a lot of results, so I'm going to take a minute to describe them. So let me start with the first controller, which is so-called naive, which is a standard MPC formulation without any extra safety constraints. So you just have the standard constraints of collision avoidance along the whole horizon. So what I'm showing you here is that for different horizon lengths, so starting from the largest one, which is 45, move into the shortest one, which is 20, you can see that the percentage of tasks failed, so task where you end up hitting some constraints, increases. And that's quite reasonable because we know that having a longer horizon improves the behavior of a standard MPC formulation. And you can see that even with the longest horizon, the naive formulation has a like 17, 18% of failure rate, and that exceeds even 50% with a shorter horizon. On the opposite end of the spectrum, we have this zero-val MPC formulation, which fails never. So you have a 0% of task failure. And the reason why it is so safe is that we impose a zero velocity as a terminal constraint. So imposing zero velocity is very constraining because the robot is always gonna need to stop by the end of the horizon. So it doesn't necessarily need to stop when moving, but it needs to be able to stop within that number of time steps. So that is very safe, but that safety is going to be paid in terms of the cost, which I'm going to show you in the next slide. And then in between these two extremes, we have different formulations, among which we have the receding, which is our own approach. And the other three are different variants of classic formulation with some terminal constraints for safety. So the terminal constraint can be soft, it can be hard, it can be coupled with some other approaches to try to get a better behavior. But what we can see is that while all the formulations, they start off quite similar for larger horizons, we can see that as the horizon shrinks, actually our approach is the one that achieves the best number of failed tasks, so the lowest number of failed tasks. Of course, safety is not all, because you also want the robot to be able to perform the task. So we should also look at another plot, which is this one, which represents how much the cost increases with respect to an optimal behavior of the system. And of course, as the horizon shrinks, the cost increases. That we know, it's expected. But what's important is that you see that the zero velocity approach, which was extremely safe, well, it's extremely inefficient in terms of optimizing the cost of the problem. And that inefficiency gets worse and worse as the horizon shrinks. Whereas our approach, that is the receding, is this one in purple. In terms of cost, so in terms of performance, is very similar to the naive formulation. So we get a much better safety with respect to naive, but we get a similar cost to it. The other approaches, or the different variants of the terminal ingredient formulation, are actually a bit better than naive and receding in terms of cost, but that's kind of reasonable because they are less constrained than the receding formulation, which has two constraints, one that is receding and one that is at the end. So it's kind of reasonable that they managed to achieve a slightly better cost, but then that is compensated by the lack of safety. Here I'm showing you a different set of simulation results where we have compared the parallel constraint MPC with receding constraint MPC and with naive MPC. So let's focus on these three dots. Let's neglect the other ones. So we can see that here we have naive, which completed less than 70% of the task and failed more than 30% of the task for this benchmark. Here instead we have the receding constraint formulation, which is much better because it completed 80% of the task while failing maybe 3–4%. But if we use the parallel constraint MPC, which exploits parallel computation for getting an improved behavior, we can see that we can do even better than that, because we can achieve an over 95% of completed task with a less than 1% of failed task. So this is extremely performant. And if you have a parallel computation, you better exploit it. All the other dots that you can see in this plot are representing different variants of the parallel constraint MPC, where we used a reduced number of cores. So we don't solve an MPC problem for each time step, but we only solve it for some time step. So maybe 16 or 8 or 4, depending on the number of cores that we have on our machine. And we show that there is a somewhat graceful degradation of performance as the number of cores that you use is reduced. Just very briefly, here I'm showing you some computation time of the different formulations. This is actually the 99 percentile of the computation time. So 99% of the time, the computation time is below these values, which you can see they are all very reasonable. So we are always below the 5 millisecond of time step, which is what we care about. Okay, so with this, I've concluded the first part of the presentation. And to summarize, I've shown you some novel MPC formulations, the receding constraint MPC and the parallel constraint MPC, which can guarantee recursive feasibility under weaker condition than the standard MPC formulation. So instead of having the requirement of having a control invariant set, these formulations can work well even with an n-step control invariant set, which is much easier to find. And actually, they can achieve even safety with weaker condition, but that's something I have not discussed, so you have to read the paper if you want to know what I mean by that. So what we are currently working on is to validate these approaches on hardware. And more towards the future, we are looking also into the certification of this n-step control invariant set, because we would like them to be certified. And also we are looking into how to handle uncertainties, which we are currently not considering. We might have dynamic obstacles that move, so you don't know exactly how they're going to move. So you can model that as an uncertainty. And also we would like to use these approaches to produce safety filters that can be used for making RL policies safe in a certifiable manner. So since that concludes the first part, I don't know if maybe you have any question about this part. It could be a good time to ask them now before I move on to the second part. Maybe nobody has questions.
If you have questions, you can also drop them in the chat and we can read them out.
Yeah, feel free to interrupt at any time. I mean,
hello, I have one quick question. This is Srijit here. So when you say parallel computation, you're expecting something like a GPU, correct? Or is it something like a multi-threaded approach?
no, it's a multi-threaded approach, what we are doing. So we suppose we have a multi-core CPU, and we allocate each core to solving one problem. We could also do that on GPUs, but that's not what we are doing at the moment.
Got it. Is that something that is explored for the future implementation in your hardware implementation as well, of using GPU-based approaches?
So we are exploring GPU-based trajectory optimization, but for this second part of my work, not in the first part yet. But I think that if it turns out to work well for the second work, then we may be using it also for the first work.
Awesome. Thank you.
Thanks to you. Any other question? Okay, then I'll be moving on. So in the second part of my talk, I'd like to talk about the efficiency side of RL. And here, the main work I'm going to talk about is CACTO, which stands for Continuous Actor Critic with Trajectory Optimization, which is a collaborative work I've been carrying out with these all amazing students and professors all around the world. We have published already a couple of papers on this algorithm and its extension, and we are still working on it because I think there is still much work to be done here. So the key motivation of this work is that reinforcement learning and trajectory optimization have very complementary pros and cons. So it seems very reasonable that we try to merge them together so that we get the best of both worlds. So on one side, we have reinforcement learning, which is much less prone to finding poor local minima when you optimize a policy. It is derivative free, and it gives you a policy as an output. So it's something that allows you to find control inputs wherever you are in state space. But that unfortunately is very poor in terms of data efficiency. On the other side, trajectory optimization has exactly the opposite pros and cons. So it's very data efficient, and it's data efficient because it exploits mainly the knowledge of the dynamics derivatives, which RL typically doesn't. But on the downside, it can get stuck in poor local minima, and it only gives you a trajectory as an output. So if your state is no longer on that trajectory, you no longer know what to do, and you have to re-optimize. So how can we put them together? Well, our idea was to start from an actor critic reinforcement learning approach, which is known as deep deterministic policy gradient, or DDPG for short, which works in the following way. You have a neural network representing the actor, another neural network representing the critic, so that's the Q function or the value function, if you're more familiar with that concept. And what you do is that you use the actor network to act in your environment. You add some noise for exploration. You acquire experience. You put all that experience in a buffer, which is known as the replay buffer. And then you sample from this replay buffer to train your critic to match the Q function of the policy that you used for acting in the environment. And then the key step for getting a better and better actor policy is that from time to time, you perform an improvement of the actor by minimizing the Q function. So every time you do that, hopefully your actor gets a bit better. And by keeping this iterative process going over and over, then you get a better and better actor. And sometimes you convert to global optimality. No guarantee, but it turns out it works well in practice. So that was the state of the art. And what we did is that we thought, how can we modify this scheme so that it's more data efficient by exploiting trajectory optimization inside the scheme? So what we did is that we introduce mainly this green block here, which is a trajectory optimization solver, which acts as an improvement step over the policy which is encoded by the neural network. So instead of using the neural network directly as a policy to act in the environment for collecting experience, what you do is that you do a rollout, so a simulation of your system using the policy represented by the neural network. And then these trajectories that you get, you use it as a warm start for trajectory optimization. So then the solver starts from that initial guess, it optimizes it until it finds a locally optimal trajectory. And that is the experience that you're going to use for the replay buffer. Another change we did is that the critic in our algorithm does not represent the Q function, but it represents the value function, because that is a lower dimensional function, so it's a bit easier to compute for us, and it makes our exploration more efficient. So for validating this algorithm, we tested it in this environment where you have this obstacle, which has the shape of a C letter. So it's a very non-convex. which makes it very difficult for the robot to figure out that if they start in this area inside the obstacle and they want to reach this blue star over here, they have actually to get further away from the goal in order to be able to go around the obstacle and reach the goal in the end. We tested this with many different kind of dynamical systems. We started simple with a 2D single integrator, then a double integrator, then a 6-dimensional car model, and finally we tested it on a 3 degrees of freedom robot manipulator. So here you can see a few examples with the 3DOF manipulator. So let's focus on the first one on the left. You can see that if you just use trajectory optimization using the initial condition of the system as a warm start, then the robot simply gets stuck inside the obstacle and is not able to reach the goal as we ask it to. So that is a locally optimal trajectory, but it's not a globally optimal one. If instead you try to use random values as initial guess, the robot is actually able to escape the obstacle, but then it does some crazy motion. So it's not still able to achieve a satisfactory behavior. If instead you use our algorithm for providing an initial guess, then you see that the robot is able to escape the obstacle and to reach the target. Notice that here you have a little collision with the obstacle, and that is because in our framework we don't have hard constraints, but actually we have only soft constraints which are just relaxed in the cost as penalties. So the robot is still able to go through the obstacle if it's convenient for it to do. So we have repeated this test for many different initial states and the 4 dynamical systems that I described before. And we have tested how often initializing trajectory optimization with the policies that we computed with our algorithm resulted in better behaviors than initializing trajectory optimization, either with random values, and that is this column here, or with the initial states of the system. And it turns out that in the vast majority of cases, our initialization was much better than using one of these 2 standard techniques. We also compared CACTO against standard reinforcement learning algorithms. So here we compared it against DDPG, actually 2 different implementations of DDPG. One was a custom one that we did. The other one, we took it from stable baseline, and also with PPO. And what we observed is that for the same training time, CACTO resulted in policies that were that had much less variance, and also that were able to achieve a much better cost in less time, as you can see here in this plot. So if I have some time left, I also have a nice 1D example, which I think is very educational to understand a bit better how CACTO works inside. But if we are a bit short on time, I can also skip that and jump to the conclusion.
I think, yeah, feel free to go over it. I think we started a little bit 5 minutes late, so it's okay to go 5 minutes over.
Okay, thanks. So let's take a very simple dynamical system. It's a single integrator. You have a 1-dimensional state, 1-dimensional control, so we can plot everything and it's easy to visualize. Suppose that your cost function C is represented by this polynomial function here, which has 3 local minima. And of course, the best one is going to be the one on the left because it's the lowest one. So if you try to solve this problem using trajectory optimization, then what you're going to get is that the optimal control input is given by this orange crosses here. And we can see that we have clearly 3 bases of attraction, which correspond to the 3 local minima that I represented before. So if you're in this pink region, then you're going to be attracted by this minimum here, and so on and so forth for the other 2 regions. So if you compute the value function that you get just with trajectory optimization with a naive initial guess, the value function is going to look like this. So you have this green function here, and then you have a discontinuity, another continuous green function here, and then you have another discontinuity, and another continuous green function here. So we can see clearly the three Bayesian of attractions, even looking at the value function. So what CACTO would do in such a simple situation is that it would compute the value function from samples, and it would try to fit the value function using a neural network. So you would get an approximation of this value function, which could be, for instance, something like this, this red line here, which represents the critic. And we can see that where we have the discontinuities in the real value function, CACTO actually makes an approximation to it because we are using a neural network which cannot be discontinuous. So everything that is discontinuous is going to be smoothed out. And this is very important because actually it's where you have these discontinuities and this smoothing effect that you're going to get improvements. And let me show you how that happens. So the policy that we have when we start is the following one. So we have the three Bayesian of attraction, and we have this different behavior of the policy in the three regions. After you go through an iteration of policy improvement, your policy, so your actor, moves from the red line to the blue line. So what happened is that in the regions where you had the discontinuities and the critic was smoothing the real value function, it's actually those are the regions where you were able to improve the policy. And we can see it if we recompute the value function for the new policy, because now the value function has improved in those regions because we went from these higher values here to these lower values here. So it turns out, and I think this is very interesting, that the fact that the critic is not able to represent exactly the value of our initial policy, but it has this smoothing effect, is really the driver of the improvement of the algorithm. So if we had an exact representation of the critic, improvements would be very, very slow or even not present at all. And this is something that actually I think is worth investigating more in the future. Okay, I'm going to stop here with this example. Let me just draw the conclusion for the second part of the talk. So what I've tried to show you is that it is actually a good idea to try to use trajectory optimization to guide the exploratory process of reinforcement learning, because we can make it much more sample efficient. And actually what we have in the paper of CACTO is that we show that adding this extra trajectory optimization step into the algorithm does not break the convergence property of original Actor Critic scheme. Recently, we have also presented an extension of CACTO where we show that we can make it even more sample efficient by using the derivative of the value function, which we can very easily compute with trajectory optimization tricks. And we can plug that derivative information into the learning of our critic to make it more data efficient. So what we are trying right now to do is to, well, first of all, try to exploit GPUs, as I was mentioning before. Now we have these very nice extensions of trajectory optimization frameworks that can work on GPUs. So using them would make our algorithm much, much faster. And also, I think that we could get a lot of speed up if we were able to bias the initial episodes of our state so that we get to explore the regions of the state space where there is more information to be collected. And finally, we would also like to find a way to handle non-differentiable dynamics, which we know is a big challenge for trajectory optimization, so we currently cannot handle. Okay, so that brings me to the conclusion of my talk. Let me just leave you with a couple of take-home messages. Overall, my goal was to show you that we can use ideas from trajectory optimization to try to improve reinforcement learning. In particular, I'm trying to making it more efficient and to making it safe. The way I'm trying to do that is at a very high level using dynamic derivatives for guiding the exploration process, and that is what I showed you with CACTO. And instead, in terms of safety, the key point is that we can use this novel safe set, such as n-step control invariant set, to make control policies that are safe with a certifiable manner. Unfortunately, we have some challenges that we need to face to make this algorithm scale to high dimensions and to tackle contact-rich tasks. And so those are going to be the focus of my future research. And with that, I have concluded. I'd just like to finish by thanking all my collaborators, which are represented here in these pictures. Thanks.
All right, thank you so much for the talk. By the way, it's Friederike here. I'm taking over for the Q&A session. So I would suggest that anyone can just unmute themselves and ask questions, or if you're more comfortable with that, you can write your questions in the chat. And maybe while people are collecting their questions, I can just kick off the discussion. So I really like I like both parts equally, but in the second part where you presented, I was wondering, you chose to go to make the trajectory optimization take information from the policy learning to initialize it. Did you also consider the other direction of trying to, or do you think you could do more to also use the trajectory optimization to help the learning, or is that already happening sufficiently, you think, through the feedback, through the training loop, or the feedback loop in your training?
A good question. They're both helping each other out. Because in the beginning, it's the actor which is helping trajectory optimization by providing an initial guess for the trajectory to optimize. But then the trajectory that comes out from the trajectory optimization solver are the ones that are used for training the critic. So the critic becomes a better critic. And then this critic is the one that guides the improvement of the actor. So you can see it that they're both helping each other out in this iterative way. So this improves that, and that improves this. And this goes on in a cycle which only stops when you converge to global optimality, actually.
Mm-hmm. Yeah, makes sense. And are you kind of initializing your actor and critic using information in the very beginning from the trajectory optimization, or you can just do random and then?
So actually, at the very first iteration, we start with trajectory optimization with a naive initial guess.
Mm-hmm.
And then we do a bit of training of the critic, a bit of training of the actor, and then we close the loop.
Mm. Cool,
So
makes sense.
we start from here, basically. We don't start from here.
Mm-hmm. Nice. So we have a few questions in the chat now, so I'm just going to read the first one.
Okay.
So the question is, there's a question for the first part of the talk, if that's okay, and of course that's okay, yeah.
Yeah.
So go ahead.
Yeah. Hi, Andrea. This is a great talk. Thank you so much. In the receding constraint NPC, after the first iteration of NPC, we are taking the first time step, first control, and then that becomes the first state in the next NPC iteration. So what happens if we're doing this in a system with pretty high uncertainties, and your next state isn't exactly where you had calculated previously? Will that affect the performance or behavior greatly? And I'm thinking about this application to systems like the biped, like humanoids. So I would love to hear your thought about this.
Yeah. So what I've discussed there is a case without uncertainties. And looking into how to handle uncertainties is something we have started to do very recently. So I have some ideas of how to do that, and I'm going to start working on that as soon as possible. But your question is very much correct. I mean, if you have uncertainties, what I've described doesn't hold anymore. So you can still try to use that scheme, and I expect it's going to work better than the standard scheme anyway. But in terms of guarantees, they're all lost. So what we are going to do instead is to empirically show that even if you add uncertainties, our scheme works better than the other scheme. That is something that we are going to do like this month.
Thank you.
Okay, do we have any more questions? So I did also have one additional question on the first part, since we're already there.
Okay.
You mentioned briefly the connection with safety filters, or using this as a safety filter.
Yeah.
When you started talking about this extension of CIS, I immediately thought about safety filters. So I was wondering, what exactly the connection is there, and how you are going, or how you think it could be used in like a reinforcement learning scenario or something.
So actually, I think the most classic approach for safety filters is to use an NPC. So, okay, so let's take this one. You use an NPC exactly like this one, but the only difference is that instead of having a cost function that really represents what you would like the system to do, the cost function is simply trying to minimize the difference between U0 and the control input given by the RL policy, which you want to filter. So basically, you're trying to check whether the policy, the action computed by the policy, it's still compliant with all these constraints, which represents the safety constraints. So as soon as you have an MPC formulation which has some safety guarantees, you can immediately get a safety filter just by changing the cost function into the function I just described. So you can do it with the classic approach where you have a terminal safety constraint, but you could do it as well with these like receding constraint or parallel constraint approaches that I've presented. It's just a matter of changing the cost function, basically. So in terms of methodology, you don't need to change anything. It's just a different application of the same idea, basically.
Yeah, okay, makes sense. Thank you.
I have one question. So would there be any idea of combining these two together? I know you talked about the actor feeding into the trajectory optimization, and if the trajectory optimization happens to be the safe MPC, would we still guarantee that CACTO can produce safe and always feasible outputs?
Okay, for sure in the long run, I think that these two trends should meet, and we should get something that is unique. However, there is a bit of a difference, which is that here we are talking about online control in the safety side of my talk. So we do MPC, whereas in the second part, we are doing offline policy optimization. So we are not doing MPC, but we are doing trajectory optimization. So what I think I would like to do to introduce safety even on that part is to add constraints inside trajectory optimization, and to account also for those constraints when I do the update of the actor policy, which currently is something that we are not doing. So in that framework, we don't have strict constraints. We just approximate them with penalties to simplify a bit our life. But in the long run, I think that we should include strict, hard inequality constraints even there. But that it's not exactly the same thing as we are doing here, because here it's a bit more difficult since it's MPC. It's not like we optimize the trajectory and end of story. We need to optimize it with this receding horizon fashion, which makes feasibility more of a challenge.
Absolutely. Makes sense. Thank you. Thank you for that clarification. Beautiful.
Thanks to you.
All right, I would suggest that since we are a little bit over time, that we stop it here. And thank you so much again for this awesome talk. It was really nice and clear talk. And I just want to remind everyone that this was the first talk of our seminar series, and there will be more announced soon. So we have, I think, 4 more talks lined up. We are just figuring out the dates. So keep an eye out for the next announcement, which will be roughly 1 per month in the coming few months. And
Well,
yeah.
thanks to you for inviting me.
And thank you all for coming too.
Bye, everybody.
Bye.